Chapter 26, electromagnetic induction is what we are going to discuss. So this is something that we have been repeatedly talking about without going into too much of details. So now in the earlier lesson we discussed how electric field and magnetic field takes part to create certain changes in the formation of a electric beam, electron beam. So now we are going to discuss more about generating electricity as well as electromagnetism and electromagnetic induction. So now in physics, the idea of conservation energy is a very important part, because we cannot create energy out of nowhere. It has to be simply transformed from one form to another. In a situation where there is a requirement for us to produce electricity, how do we do that? Now, in all of the mechanisms with which we produce electricity, there is a turning of a turbine involved. Whether it be hydroelectric power, wind energy, or nuclear energy, what we do is we simply get a turbine to rotate. In hydroelectricity, directly the power of flowing water will turn the turbine. In other situations, in diesel and nuclear energy, what we do is we use the nuclear power or the heat energy that is produced by burning fuel oil to boil water, and that steam is used to, that steam would be pumped through high pressure tubes to rotate the turbine. And in wind energy turbines like this, what we do is we simply use the wind power to turn the turbine. So that wind power, the turning turbines, will make through a magnetic conducting wire. So we have discussed so far about how electricity can be produced when a conducting wire goes through a magnetic field. So when the conducting wire goes through the magnetic field, when it is rotating, so it cuts this magnetic field, thereby creating the force. So this force in turn will produce electricity. So that is basically the principle that lies behind electromagnetic induction. So what we do is, first of all, we have to observe how this induction takes place. So what we do is we connect a small electric motor to a moving coiled voltmeter. Then we spin the shaft of the motor, and we will be able to see there would be a reflection on the voltmeter. So what happens is there is, when we connect the motor to a power supply, it turns. But here what we have done is we have turned it without connecting it to a power supply. So that has resulted in production of a power. So that is exactly the electric motor working in reverse is the generation of a power. Or if you connect it to a power source, it will rotate. So that is basically the idea in this. Then this is again another thing. Since we use a sensitive micrometer and connect the micrometer to a coil, and then we move a bar magnet in towards the coil, and we hold it still for a moment and then pull it back. Then we will see when we move it, there would be a reflection on the micrometer. Then if we connect it, if we stop it from moving, then there wouldn't be a a deflection. So you can you probably remember these kind of microammeters, how to use them, and how you can get a better reading. So those are all part of this lesson, and you should be able to explain it further. When you increase the speed, what will happen? When you decrease the speed, what will happen? When you bring it to a stop, what will happen? These are things that you need to understand. So obviously you would know when the speed is higher, it would create a higher deflection. If the speed is lower, it would cause a lower deflection, and when it is stopped, there wouldn't be any deflection at all, meaning that there is no induction of current in this. Then the third one is you connect a long wire to a sensitive microammeter. Then you move the middle section of the wire through a magnetic field between two magnets. You place it across a magnet like this, and then move it up and down. So you know that in this kind of a bar magnet, if I am to draw it like this, so this is the cross section of the magnet, then you would know that the field lines would be placed like this. And then if I am to draw the wire, the wire would be like this. Wire would move up and down like that. I hope it makes sense to you. So the wire would move up and down like that, thereby cutting the field lines. So that induces a current on that. So then obviously there would be a deflection on the microammeter. So these are all the three. These are three different ways of investigating the induction of a current when a wire moves through a magnetic field. So then there would be many factors that would affect the induced EMF. EMF stands for electromotive force. In all of these, all the three practicals that we discussed, there is an electric current caused by the induced EMF. So there is no power source, but we created power by cutting the conductor through the magnetic field. So now if we stop the movement, the current stops. So if we increase the strength of the magnetic flux density B, what will happen? It will be higher. So if we are talking about a straight wire, magnitude of the magnetic flux density will affect the EMF. Then length of the wire in the field, once again, if the length is higher, then the EMF is also higher. Speed of the wire moving across the magnetic field, once again, it is much higher if the speed is higher. For a coil, the EMF would depend on again magnetic flux density, cross-sectional area of the coil. If the cross-sectional area of the coil is higher, then there would be higher EMF. Angle between the plane of the coil and the magnetic field. So it should be 90. If it is 90, it is the highest. Number of turns of wire. If the number of turns is higher, then again there would be more length in it. That is exactly what it means. Then rate at which the coil turns in the field, once again it is the speed of the wire moving across this. So all of these things will increase. If they increase, there is a direct relationship. If they increase, the EMF will also increase. I hope that you understood that part. Let's move on to the next part as well, and after that we will write down a note. Now we have seen from the practicals that we discussed that a movement of a conductor in a magnetic field induces a current in the conductor. However, it has to be a complete circuit. That means it should be connected. All parts need to be connected in a circuit. We used now in this particular situation, in the first one, what happened was the motor was there, and the voltmeter was there. So the voltmeter connects the entire system. So the motor is connected in either two ends. We can't just connect with one wire. It has to be connected both ways. If the circuit is incomplete, then of course there wouldn't be a current to flow. There has to be a PD, potential difference between the two. So now the meter was used. So you know that if there is no potential difference, there is no flow of electricity. So that is another important aspect that you need to keep in mind when trying to understand these things. Now, when you take a simple bar magnet, it has a field line like this. It has a field like this. Now also remember, this is just a plane view that we have shown. So this is a 3D object. So it has three-dimensional point to it. So that is also something that you must remember. Now, if we move it to the if we move a wire through this magnetic field, it cuts across these magnetic field lines. If we move it one way and if we move it in the opposite direction, it gives rise to current caused by the EMF in the conductor. If it really doesn't, it doesn't really matter whether the conductor is moved through the magnetic field or the magnet is moved past the conductor. The only thing that needs to happen is there are two things that you can do. You can move the magnet or you can move the conductor. However, whatever you move, there would be an EMF induced. The only thing is, condition is that the field lines need to be cut when going through that, when going across that. So when you are making a motor or a generator, if moving the magnet is easier, then you can move the magnet. If moving the wire is easier, you can move the wire. Whatever it is, you have to make sure that the wire is cut by the magnetic field, or rather magnetic field is cut by the wire. If we use a coil of wires, for a coil of n turns, the effect is n times greater than a single wire. Right? So that is obvious. So that means if now I'm just making an assumption. If a single wire makes a current of 0.1 ampere to flow, then if it is 2, then it would be 0.2 amperes. If it is 10, it would be 1 ampere. If it is 100 turns, then it would be 100 amperes, something like that. So you need to understand that higher the number of turns, higher would be. That means there would be 100 wires moving at a particular given instant. Then if there is a change in the EMF, if there is a change in the number of field lines, that links the coil, if there is a change in the number of field lines that pass through the coil, we say that an EMF will be induced across the ends of the coil, or else there will be a current caused by the induced EMF, or else, in other words, there would be a current flowing. If once again the condition is that it has to be a complete circuit. So now in the next diagram 26.6, I suggest that you look at it. It shows a coil near a magnet. So there is a coil near a magnet here. Then there is a coil outside the field, right? So it does not link to any of the field lines. When the coil is outside of the field, no magnetic field lines link the coil. When it is inside the field, there are field lines linking the coil. If you move the coil into or out of the field, then an EMF is induced. If this is actually This is actually the basic understanding, but again we need to understand what magnetic flux is to get a clearer understanding of how EMF is able to generate, how EMF is generated in a circuit. But in a basic principle, what you need to understand is the coil needs to be either moved in or out for the power to be generated. Now, when you are talking about especially when you give an answer for the first question, you would have to talk about the induction of the EMF due to the movement or the magnetic field being cut by the conducting wires. So I think you would be able to write a very good answer for that. If you have any doubts, please ask me. Let's write down a note before we move on to the other parts of the lesson. Write down induction, subheading observing induction, experiment 1. A small electric motor is connected to a moving coil voltmeter. When the shaft of the motor is spun, a deflection is observed in the voltmeter. This is because the magnets inside the motor has a field which is cut by the coil of the motor, which induces an EMF and makes a current flow through the complete circuit. Experiment 2. A coil is connected to a sensitive microammeter. And a magnet is moved in and out of the coil. When we move it in and out, there would be a deflection. However, if you stop, there wouldn't be any deflection at all. Experiment 3. A wire, a long thin wire, is connected to a sensitive microammeter and moved through a magnetic field. There would be a deflection which suggests that an EMF induces a current when the wire is moved through the field. Then subtopic, factors affecting induced EMF. For a straight wire, we will write for a straight wire, and under that please write down number 1, magnitude of the magnetic flux density. Number 2, length of the wire in the field. Number 3, speed of the wire moving across the magnetic field. in front of all those three, or underneath that, put a star and use a different colored pen and write down. For all three, when they increase, the EMF increases. That is a direct relationship. Then leave a line and write, for a coil of wire, number one, magnitude of the magnetic flux density, cross-sectional area of the coil, angle between the plane of the coil and the magnetic field, number four, number of turns of wire, number five, rate at which the coil turns in the field. Then write down, electromagnetic induction occurs when a wire is moved into a magnetic field and cuts across the magnetic field. Write down, either the magnet could be moved or the coil could be moved. All which is required is for the magnetic field to be cut by a conducting wire. Leave a line and write, this effect can be easily observed if a coil of wire is used. For a coil of n turns, the effect is n times greater than for a single turn of wire. I hope you understood. If you have any questions, please ask. If you did understand everything, please do question number 1.